All right, so let's take a look at this section, 3.9 related rates. Yeah, here it is in the book. So this is another application of the chain rule and implicit differentiation. So yeah, I made some notes. All right, so what's the idea? So we have two quantities, and if they're related, then if you change one, it's going to change the other, so that their changes have to be related. And yeah, here changes, that's we're talking about rates of change, so derivatives. Let's see an easy example to start with. So let's say our quantities are a side length x. Okay, so we're talking about a cube here. Okay, that's supposed to be a cube. So if you know the side length of a cube, then its volume is easy to get. It's just going to be x cubed, x to the third power. For example, if the side lengths here, so if this is, oops, so if this is 3 feet, this is 3 feet, and this is 3 feet, okay, so all these are 3 feet, then the volume is 27 cubic feet. Okay, so suppose this box is increasing, changing with time t. Okay, so suppose the side length x is increasing. So what's the corresponding change in the volume? Okay, so if we know dx dt, can we find dv dt? Okay, so the idea is to apply ddt to both sides. Okay, so just like we did with implicit differentiation, here we're thinking of x as a function of time and v as a function of time. Okay, so implicitly these are two functions of t, and we just apply ddt. Okay, so we want the change with respect to time. Okay, well dv dt, that's just the change in the volume. But here we have ddt of x cubed. Okay, so the outside function is cubing, the inside function is x of t. Okay, so here we need the chain rule. Okay, so we get the derivative of the outside function times the derivative of the inside function, right? So dx dt. All right, so these are the related rates. So the rate of change of the side length is related to the rate of change of the volume. And it's not a straight equality. Yeah, so the bigger x is, the more the volume's going to change for the same change in the side length. So the bigger the cube gets, the more the volume's going to be changing. Okay, so we have this relationship. So for a specific question, if the sides of a cube are increasing at 2 inches per second, what is the rate of change of the volume of the cube when the side length is 10 inches. Alright, so we're just substituting into this formula. Okay, so we're looking for the rate of change of the volume. So that's dV dt. That's what we're looking for. So it's 3. Okay, we're told the side length is 10, so this is x. So x is 10, so we need 10 squared. And dx dt, well, we know that's 2 inches per second. Okay, so you just have to kind of decipher the question. What we're using all the information here, just putting the numbers into the formula, into the correct place. And if I did this right, yeah, this is 600. Yeah, so the volume is, yeah, the units are inches, so the volume, yeah, so length is in inches, area is in square inches, volume is in cubic inches, and T is measured in seconds, so it's cubic inches divided by seconds. Okay, so when the box is this big, the volume is increasing at 600 cubic inches per second. Okay. All right, so that's what we're up to. Yeah, let's go from cubes, 3 dimensions, down to a bit easier rectangles, 2 dimensions. Okay, so we know the area of a rectangle. So if you have width W and length L, then the area, the space inside, is measured by A is equal to L times W. So just a product. Here's the question. If the length, the rate of change of the length is 8 centimeters per second. Okay, so this length is increasing. The width is also increasing at 3 centimeters per second. Okay, so this rectangle is growing pretty quickly. Then how fast is the area increasing when the length is 20 centimeters and the width is 10 centimeters? Okay, so we're given this information, and yeah, we're looking for how fast is the area increasing, so we're looking for dA dt. Okay, so this is the key equation, and just like before, we're going to hit both sides with d dt. Okay, so A, L, and W, think of these as 3 functions that depend on time. All right, so here, so d dt of A, that's just dA dt. Here we have a product, so d dt of L times W, these 2 functions of t, we need the product rule. So it's L times dW dt plus W times dL dt. Okay, so the a nice application of the product rule. All right, so this is what we're looking for, and it's equal to this, and we're given all these quantities, so then just substitute. Again, the rate of change of the area depends on how big the rectangle is. So the bigger L and W are, the bigger the rate of change of the area. Okay, so here's L is 20, W is 10. Yeah, units are centimeters here. dW dt, so the width is increasing at 3 centimeters per second, dl dt. So just put these in the formula. And yeah, 60 plus 80, 140. Yeah, it's an area, the change of the area over time, so that's the units are square centimeters per second. And yeah, this, for these kind of word problems, yeah, right, don't just put a number, yes, well, include the units and also some words explaining what the numbers mean. And so the area of this rectangle is increasing at a rate of 140 square centimeters per second. All right, so that's making sense. Okay, so here's one for you to try. Our two quantities, x and y, are related by this formula. So y is equal to the square root of 2x plus 1. X is changing, so dx dt is 3. The question is to find dy dt when x is 12. Okay, so no units to worry about here. All right, so you can pause the video, see if you can do this one. So again, just apply ddt on both sides. And yeah, the chain rule is going to be needed. Okay, so give it a try. Okay, so let's see, how does this work? So ddt on both sides, so yes, so we get, yeah, just dy dt here. On the left, on the right, ddt, of course, yeah, this is a 1/2 power for the square root. So the outside function is this 1/2 power. So it's 1/2 of the inside with a 1/2 minus 1 power times the derivative of the inside. Okay, so x is a function of t. Well, this part, yeah, so ddt of 1 is 0, that goes away. You can bring out the 2, so we're just getting dx dt times 2 for the derivative of the inside. All right, so this is what we're dealing with. Yeah, these, we've got to get 2 times 1/2, so these cancel. Minus 1/2, so that's 1 over the square root of 2x plus 1. Okay, so this part simplifies to this, rewriting it with a radical. Okay, then just substitute. So from the question, yeah, we were told dx dt was 3, and we're interested in the rate of change when x is 12. So this is the square root of 25, right? All right, so dy dt is 3 over 5. Okay, so that was an easy one. But yeah, that's those are the main ideas. Applying ddt on both sides. Chain rule. Alright, so let's see a more difficult one. So this requires a bit of setting up. Okay, so we have this word problem. Example 4. A 10-foot ladder rests against a vertical wall, but the bottom of the ladder is sliding out at 1 foot per minute. How fast is the top of the ladder moving when the bottom is 6 feet from the wall? So yeah, we definitely better draw a diagram. Okay, so here is the ladder. Okay, resting against a vertical wall on a presumably horizontal ground. But the bottom of the ladder is sliding out. Okay, so if the bottom slides out, the top is going to slide down. So that's the question. How fast is the top of the ladder moving when the bottom is 6 feet from the wall? Okay, so we certainly have a right angled triangle if this wall is straight. So we can use the Pythagorean theorem. A squared plus b squared equals c squared. The hypotenuse here is 10. Yeah, the units are feet. So let x be the distance from the bottom of the ladder to the wall, y the distance from the ground to the top of the ladder. Alright, so this is the equation we're dealing with. Yeah, so for this one we had to come up with our own equation from the question. But yeah, often these types of questions you've got a right angle triangle, so just remember the Pythagorean theorem. Okay, and then hit both sides with ddt to find the related rates. On the right it's easy. ddt of 100 is 0. This is just a constant. Okay, here we have a sum. So it's ddt of this plus ddt of this. Okay, the outside function is squaring, and the inside function, think of x as a function of t, so the inside function, the derivative of the inside function is dx dt. And this is exactly the same with y's. Okay, so what am I saying here? So the last step is to substitute we're substituting the information here into this so this equation, so this is equal to 0. Okay, so what do we know? So x, how is x changing? Okay, so the bottom is sliding out at 1 foot per minute. Okay, so the bottom is moving at a constant rate of, so dx dt is 1. And we want to know, so we're looking for dy dt, the rate of change of the top, when x is 6. All right, so that's what we're substituting. Yeah, this is our equation. So x is 6, dx dt is 1. We're looking for dy dt. Some extra work to do here, though. So what is y? So yeah, we have to go back to the Pythagorean theorem. So if x is 6, hypotenuse is 10, we want to figure out y, so yeah, we have to go back to the original equation. So put in x equals 6 here to find y. So 36 plus y squared equals 100. So y squared is equal to 100 minus 36, 64. So y is plus or minus the square root of 64. Okay, here y is plus, so plus 8. All right, so yeah, a bit of work to find the y, but y has to be 8 when x is 6. All right, so now a nice linear equation to solve for dy dt. Yeah, you can divide through by 4. So 3 plus 4 dy dt equals 0. Subtract 3, divide by 4. All right, so dy dt, the rate of change, so y is the height of the top of the ladder, so that this height is decreasing. Its rate of change is for this position, the rate of change is minus 3 over 4. It's negative. That means the height is decreasing, not increasing. So in words, the top of the ladder is moving down at 0.75 feet per minute. Those are our units. When the bottom of the ladder is 6 feet from the wall. All right, yeah, so that was a more complicated one. It's a fairly standard kind of question, though, and yeah, we'll see other ones that are similar. But yeah, certainly convert this information into a diagram. Yeah, we've got our ladder resting. The Pythagorean theorem gave us the equation. Okay, we have two related quantities, x and y. They're related like this. And then their rates of change are related by this equation. And substituting gets us dy dt. Okay, moving on to the next one. Yeah, this is the real classic calculus problem. Two cars start off from the same place. One goes north at 60 miles per hour. One goes east at 25 miles per hour. Okay, very slowly. How is the distance between them changing 2 hours later? Yeah, this is a classic. So a similar kind of diagram. Yeah, so the two cars start together. This car is moving north. Okay, so let's give its position. So the distance it's traveled north is y miles. The other car is traveling east. Let's say it's gone x miles. And we're interested in the distance between the two cars, so we're looking for this length. Pythagoras to the rescue. So yeah, x squared plus y squared equals d squared. Yeah, capital D. So d itself is the square root of x squared plus y squared. Okay, so this is our basic equation. So yeah, so there are three quantities. The position of each car and the distance between them. And all three are changing. So yeah, what we're after is, yeah, so how is the distance between them changing 2 hours later? So that's d capital D dt, that's what we're after. Okay, so we're applying d dt on both sides. So yeah, so we need d dt of x squared plus y squared to the power 1/2. So that power 1/2, that's square root, that's the outside function as before. Power goes down by 1, and we need d dt of the inside function, x squared plus y squared. Okay, so this, yeah, we did this, we just did this one. So that's, again, another application of the chain rule. So it's 2x times dx dt plus 2y times dy dt. Yeah, just like in the last example. Okay, so this is looking, it's similar, but just a bit more complicated. So, yeah, there was some simplifying. Yeah, so the multiplying by 1/2, so these, it's 1/2 times each of these, distributing, yeah, these cancel. Write this as 1 over the square root of x squared plus y squared. And so this is on top. And this is our formula relating all the rates. Dx dt, that's the speed of the car going east. Dy dt, that's the speed of the car going north. So we were given those two. They're going at these constant speeds. And yeah, what was the question? How is the distance between them changing 2 hours later? Okay, so they start off from the same place. 2 hours later, what's the situation? So yeah, so the first car, it's going north at 60 miles per hour. So after 1 hour, it's gone 60 miles, but after 2 hours, it's gone 120 miles. Okay, so 2 hours later, y is 120. Okay, that car's gone 120 miles north. 2 hours later, the car going east it's only gone 50 miles. Okay, so yeah, here we're using the distance is equal to time times velocity. Okay, so we get the numbers to substitute. X is 50, y is 120, dx dt is 25. Okay, so, and then substituting, if I work this one out right, d dt So 2 hours later, the distance between the cars is increasing at 65 miles per hour. Okay, so does that make sense? So if the cars were traveling in opposite directions, 60 miles an hour and 25 miles per hour, then the distance would be increasing at 85 miles per hour. But yeah, they're not going in opposite directions. They're going at right angles. So yes, expecting something less than 85, and yeah, more than 60. So yeah, this example, this number is plausible. And the units, yeah, the distance units are miles, time is in hours. 65 miles per hour. Yeah, this is a real classic type of problem. This could well come up on tests. The Pythagorean theorem was needed to set it up again. All right, one more example. Example 6. A camera is positioned 2 miles from the launch pad of a rocket. It tracks the rocket as it launches. Okay, this time we're interested in the rate of change of the camera's angle, theta, when the rocket when its speed is 500 miles per hour and the angle is pi over 3 radians, so that's 60 degrees. You remember, our angles are always measured in radians in this class. Okay, so this camera, it's tracking this rocket. One more right angle triangle, but this time it's some trigonometry we need instead of Pythagoras. Yeah, so we're not interested in the distance here, we're interested in the angle. Okay, the camera is 2 miles from the launch pad. Yeah, we're assuming this rocket is shooting up vertically. The height of the rocket is y miles, and the angle is theta. And we're interested in when the angle is pi over 3, so about 60 degrees, or exactly 60 degrees. And the rocket, this is the rocket here, blasting off when its speed is 500 miles per hour. So what is the rate of change of the angle? So how fast is the angle changing? So here we need to remember some basic trigonometry. Yes, so tan of an angle, so tan is the opposite over the adjacent. So tan of theta is y divided by 2. Okay, so instead of Pythagoras, we're using just basic tangent ratio. So this relates the two quantities, the height of the rocket and the angle for the camera. As usual, apply d dt. So this time the Outside function is tan, so we need secant squared for its derivative. The inside function is theta as a function of t, so that's d theta dt. Okay, so a different, so using our differentiation formula for tan, here it's easier, we just have a constant, so we're just getting 1/2 dy dt. Okay, so dy dt, so the rate of change of the height of the rocket, that's 500 miles per hour. We're looking for d theta dt, the rate of change of the camera's angle. Okay, so we can solve, so just divide both sides by secant squared theta. And yes, slightly easier to use cosine, so secant is 1/cosine, so we're flip that over. D theta dt is cosine squared theta divided by 2 times dy dt. And the last step, just substitute what we know. So yeah, so cosine of pi/3, cosine of 60 degrees is 1/2. A special angle, dy dt is 50. So we have 1/2 squared divided by 2, so 1/4 divided by 2, that's 1/8 times 50 times 500 is 62.5. Okay, so what does this number mean? Yeah, that's d theta dt. Yeah, theta measured in radians, t measured in hours. Okay, yeah, so units are hours here. So this should be our angle is changing at 62.5 radians per hour. Yeah, important to get the units right. So yeah, just if time is being measured in hours, then yeah, that's the bottom unit here. All right, so I hope that made sense. So related rates. Take a look at the homework questions for this section.